A black hole is not a hole. It is an object in space. It has mass, just like a planet or a star. But it is different from anything else in the universe because its gravity is so strong that nothing can escape it. Not a rocket, not a radio signal, not light, and light is the fastest thing that exists. Every object with mass has what is called an escape velocity. That is the speed something needs to reach in order to leave that object and not fall back. From Earth, that speed is about 11 kilometers per second. A rocket that reaches that speed can leave Earth completely. From the surface of the moon, the escape velocity is lower because the moon has less mass. From a black hole, the escape velocity is higher than the speed of light. Light travels at 300,000 kilometers per second. Nothing moves faster than that, so nothing escapes. That is what a black hole is, an object where the escape velocity exceeds the speed of light. Black holes were not found by looking through a telescope. They were predicted by math. In 1915, Albert Einstein developed a theory called general relativity. It described how mass affects space and time. The math correctly predicted how planets move, how light bends near the sun, and how clocks run at different speeds depending on gravity. But the same math also showed that if enough mass were packed into a small enough space, gravity would become so extreme that nothing could get out. For a long time, scientists argued about whether this was a real physical thing or just a quirk in the equations. It turned out to be real. Here's what's actually happening with gravity, because most people have the wrong picture of it. Gravity is not a force that reaches out and grabs things. It is what happens when mass changes the shape of space around it. Mass bends space. Objects then move along that bent space. The Earth does not pull the moon toward it with an invisible hand. The Earth bends the space around it, and the moon follows that bend. Once you have this picture, everything about black holes makes sense. With the old picture, it does not. As mass increases and size decreases, that bending gets more extreme. The escape velocity goes up. A normal star has high gravity, but light can still escape. If you compress that same star into a much smaller space, the escape velocity keeps rising. At some point, it exceeds the speed of light. At that point, you have a black hole. If you fired a beam of light directly away from a black hole, it would still not escape. It would slow down, stop, and fall back in. Not because something grabbed it, because the shape of space itself curves everything inward past a certain point. Every black hole has a boundary around it called the event horizon. This is not a wall. You cannot see it or touch it. It is an invisible line. On one side of that line, you can still escape if you move fast enough. On the other side, every possible path through space leads inward. There is no direction out. The event horizon is the point of no return. Crossing the event horizon does not feel like anything special. If you were falling into a very large black hole, you would cross that line without noticing. No alarm goes off, no barrier hits you. You only know you crossed it when you realize that no matter which direction you move, you keep getting closer to the center. At the center of a black hole is something called the singularity. This is where all the mass ends up after the collapse. The math says the density there is infinite. When a calculation produces infinity, it usually means the math has hit its limit. That is what is happening here. Our best theory of gravity stops working at the singularity. We do not actually know what is there. It is an open problem. This is the important part. Here is how a black hole actually forms. The most common type starts as a very massive star, at least 20 times heavier than our sun. Stars stay alive by burning fuel through a process called nuclear fusion. Fusion pushes outward. Gravity pulls inward. As long as fusion is happening, those two forces balance. When the fuel runs out, fusion stops. The outward push stops, gravity wins, the core collapses in less than a second. The outer layers explode outward in what is called a supernova. What is left at the center is so compressed that it becomes a black hole. Not every dying star becomes a black hole. Smaller stars like our sun end as much less dense objects. You need a very massive star for the collapse. To be extreme enough, there are two main types of black holes. Stellar black holes are a few to a few dozen times the mass of the sun. They form from dying stars. Supermassive black holes sit at the center of almost every large galaxy, including ours. They contain millions or billions of times the mass of the sun. The one at the center of our galaxy is called Sagittarius A star. It contains about 4 million times the mass of the sun. How supermassive black holes got that large is still being studied. Gravity does not just pull things, it also slows down time. The stronger the gravity, the slower time passes. This has been measured and confirmed. GPS satellites orbit Earth at a height where gravity is slightly weaker than on the ground. Because of that, time moves slightly faster for those satellites than it does for us. If that difference were not corrected for in the software, GPS would give you a position that drifts by about 10 kilometers every day. The correction is built in because the effect is real. Near a black hole, this effect is extreme. If you watch someone fall toward a black hole from a safe distance, you would see their clock slow down and eventually appear to stop right at the event horizon. From their point of view, their clock runs normally. Both things are true at the same time, just from different positions. Gravity also does not pull evenly on all parts of an object. It pulls harder on the side that is closer to the source. On Earth, the difference between the pull on your feet and the pull on your head is so small you never feel it. Near a black hole, that difference can become enormous. Like the side of your body closest to the black hole gets pulled much harder than the far side. This stretches objects. For stellar black holes, which are small and dense, this stretching force is extreme even at the event horizon. You would be pulled apart before you crossed it. For supermassive black holes, the event horizon is much farther from the center. The stretching force there is mild. You could cross the event horizon without being harmed. In 1974, a physicist named Stephen Hawking showed that black holes do slowly lose energy over time. Quantum mechanics, which is the branch of physics that studies extremely small particles, shows that empty space is not actually empty. Pairs of particles constantly pop into existence and annihilate each other everywhere in space. Right at the edge of a black hole's event horizon, one particle from a pair can fall in while the other escapes. The black hole loses a tiny amount of energy each time this happens. Over an unimaginably long time, a black hole could lose all its mass this way and disappear. For a black hole the size of a star, that timescale is longer than the current age of the universe by a huge margin. It is real physics, but it has no practical effect on any black hole that exists today. What makes it important is that it connects two theories of physics that otherwise contradict each other when used together. Since light cannot escape a black hole, we cannot see one directly. We detect them by watching what they do to everything around them. When gas and dust fall toward a black hole, they do not fall straight in, they form a spinning disk around it. As the material in that disk rubs against itself, it heats up to millions of degrees. At that temperature, it gives off X-rays. Astronomers detected these X-ray signals in the 1960s and 1970s and traced them to regions where a normal star appeared to be losing mass to something invisible. The only explanation that fit was a black hole. In 2015, a detector called LIGO picked up ripples in space caused by two black holes colliding and merging. These ripples are called gravitational waves. They had been predicted by Einstein's math but never directly detected before. In 2019, a network of radio telescopes called the Event Horizon Telescope produced an image of the region around the supermassive black hole in a galaxy called M87. In 2022, it did the same for the black hole at the center of our own galaxy. Let me show you exactly how this works by running through one sequence from start to finish. A massive star runs out of fuel. Its core collapses. The escape velocity at that point exceeds the speed of light. An event horizon forms. That is the point of no return. Material nearby does not immediately fall in. It orbits, just like planets orbit the sun. Over time, some of that material spirals inward. It forms a hot spinning disk. That disk glows in X-rays. An observer watching from far away sees the light from material near the event horizon appear to slow down and shift toward red. That happens because light loses energy when it tries to climb out of a very deep gravitational field. Less energy means a longer wavelength, which means a shift toward red. Every concept covered in this video is present in that single sequence. They are not separate ideas, they are different parts of the same thing. Here's what people most often get wrong. The most common mistake is thinking that black holes pull everything nearby into them like a drain. They do not. I mean, if the sun were replaced by a black hole of the same mass right now, Earth's orbit would not change. Earth would keep going around it the same way it does now. Black holes only capture material that actually gets close enough to cross the event horizon. Everything else stays in orbit. A second mistake is thinking the singularity at the center is the dangerous part. The event horizon is the point of no return. The singularity is what is waiting at the center after you have already crossed a line you cannot come back from. The boundary is what matters, not what is inside it. A third mistake is thinking that because we cannot see black holes directly, the evidence for them is uncertain. It is not. The evidence comes from orbital motion of stars, X-ray emissions, gravitational wave signals, and direct imaging. These are completely separate methods that all point to the same conclusion. When you read a news story about a black hole merger being detected, you now know what that means. Two objects of extreme mass came together, and the distortion in space from that collision spread outward like a wave and was picked up by a detector on Earth. When you see an image of a glowing ring around a dark center, you know the ring is superheated, gas spiraling inward, and the dark center is the region nothing can escape from. When a story says a black hole contains 1 billion solar masses, you know what that means, in terms of gravity and the size of the boundary around it. You also know where the open questions are. The singularity is where our math breaks down. Hawking radiation is where two major theories of physics need to work together, but currently cannot, without producing contradictions. These are not signs that physicists are confused. They are the known edges of what current theories can handle. You can now describe what a black hole actually is, how one forms, where the point of no return is, and why it exists, why time slows down near extreme gravity, and how we confirm the existence of objects that cannot be seen directly. That is a complete picture. It is what this topic should have looked like the first time you encountered it.